Hello everyone. In this video, I am going to show you how to conduct measurement invariance with dyadic data using Mplus. And so in this video, I will strictly kind of go over the syntax and the interpretation of the results, and I will briefly describe some of the details around the various invariance steps that we're going to be taking. However, I will not go into a whole lot of extra detail around those steps. Those will be available in a separate video. And so we are going to shift over to Mplus. And so what you will see here is the syntax for the configural model. And so I'll briefly walk you through some of the basics of Mplus. So you have a title up here, and so I'm just calling it measurement invariance. You can make your title as long as you want. This is actually a place where I'll frequently make notes on the different data sets that I'm using, on notes around the model or whatever it is. So it can be as long as you want. So use the title space for note taking, and you'll also see I do some annotations in my work as well, but I find that to be really helpful. The second line is your data line. And so in Mplus, if you have your data file and your syntax file in the exact same folder, then all you need to do is type in the data colon, and then you say file is, and then the name of your data file. If your data file and your syntax file are in different folders on your computer, then you will need to go in and you will need to specify the exact location of it. So what that will look like here is I'll go into a different folder and I'll right click and it'll say copy as path. And so I'll minimize this, get back to Mplus, and then I paste it. Then that is the path, and that's what you will have to do. So I always make sure I don't have to do that because it's kind of a pain in the butt, especially if you use external hard drives and things like that for your data files to securely store your data. So I'd be sure that everything is in the same folder. So that's just a habit I've developed over the years, but there are certainly other ways to do that. So the next is your variable command. And so you will start off with variable and then a colon and then names are, and all of these are the variables that are in the data set. All right. And so what you will notice is that every variable that is designated for a male has underscore M at the end. And so for this variable, this is a level of education for the male partner. And then if you go down here, I have educate, and it doesn't have the underscore M. That indicates that it's for a female partner. So implicit to this is that these data are in wide format. So I have all my male variables, the first, let's say 60 columns, and then my female variables are the next 60 columns. All right. And so on each row, I will have a dyad ID. And so each row will consist of only one dyad. And again, because it's in wide format, you have the male and female partners on that row. So if my row was 13, or that's the dyad number, then I would have the male level of depression, for example, and I have the female level of depression. If the data were in long format, then I would have two lines for the dyad ID. I would have dyad ID 13, and that would be for the male, and then I have dyad 13 again, and that would be the female, and their levels of depression would actually be in different rows within the data file. Okay, so I believe ubiquitously all SEM, to the best of my knowledge, uses a wide format. And if you use multi-level modeling, you will be in long format. Again, I don't know of any SEM packages or programs that use long format for structural equation modeling. So the next is going to be use variables. And so sometimes, or perhaps even by design, you might only include your variables that you're going to use in your present analysis. But oftentimes, especially when I'm engaging in model building, I'll first start off with a structural model, which is what we're going to talk about today within a CFA framework, and then I'll gradually add in predictors. So I want to build a bigger data file with all of my variables that I'm going to potentially use, rather than having to go back in and keep adding those one by one. And so I use the use variables command so I can have that bigger data set, and I'm telling Mplus here, I only want to use these 10 variables, right? So Mplus is going to automatically exclude every other variable from the analysis, and we're only going to use these 5 items on the relationship mindfulness measure for males and for females. This data set has very little missing data. We're roughly around 98, 99% complete, but we do have those scattered missing values, and so I've coded them in SPSS before I move the data over to be -999. And I am just telling Mplus to look for those -999s and recognize those as missing. Because if Mplus sees that -999 and I don't have this command in there, it doesn't know that that's a missing data command, and it is going to believe that is an actual value, and that is going to really, really mess with your results. So when you get screwy results, oftentimes it's due to a syntax error somewhere, and a lot of the times it's going to be because you specified, or you didn't specify your missing data command, or you have multiple missing data values and you only specified a subset of them. Right? I'm a big fan of having some form of ID variable in Mplus. I do a lot of sensitivity analyses when I'm looking for outliers. If I'm able to have this ID variable in there, then it'll tell me which cases are potentially outliers, which cases are potentially influential, and it allows me to really easily kind of drop those cases from my analysis. And so I always have an ID variable somewhere in my data set. So your analysis command, actually in this analysis that we are running a confirmatory factor analysis with a focus on measurement invariance, we actually don't need anything in here. So if you just ran Mplus like this, it should be fine. I just have it here more for illustrative purposes. ML means maximum likelihood, and that's going to be the default for Mplus in all your analyses, unless you specify otherwise or are using some other more advanced set of estimation procedures. All right. And so now getting down to the model command. So in the model command, this is where we're specifying our actual statistical model. And so what we are going to do first is we're going to specify the latent variables for male and for female. And so what we are going to do is create a name for the latent variable. And so I'm calling it RMM_male because it's the relationship mindfulness measure, and I'm doing the _male to indicate the gender. All right. And I'm using a by statement here. So in Mplus, this means that all variables following the by statement are going to be factor loadings. And so that's one way Mplus differentiates factor loadings from regression coefficients from covariances, is by using that by statement. And then I will just simply enter in the variables one after another. So if you're a Lavon user, you're probably used to the equal sign and then the tilde. The equal sign and the tilde. In Mplus, we don't do that. We use the by statement, and you're probably used to the plus signs in between. Also in Mplus, we do not do that. You can just list off all of your variables. So in many analyses, I find Mplus syntax to be far more compact than in Lavon or in R more generally. So the next thing we're going to do is specify the relationship mindfulness latent factor for females, and we are going to do the exact same thing, that same by statement as above, and we have those same 5 items for the females who participated in the study. And our sample is only of cisgender heterosexual couples. And so we don't have any gay or lesbian couples or transgender individuals just for the sake of measurement invariance, because we have to put people into groups in order to conduct measurement invariance. And oftentimes it's either exceptionally difficult to put people into groups due to their identity occurring on a spectrum, for example. So like if we're doing measurement invariance across age, it's going to be exceptionally difficult if we have people between the age of 18 and 70 in the study to put people into those groups. And so that's why I chose to do that. And also, when conducting measurement invariance, we are going to need we might not have the statistical power to conduct really small subgroups. So I think in the actual data set, there's only 3 or 4 gay couples. I think there's 3 or 4 lesbian couples. And so there's not statistical power to detect any differences if they were actually there or not. And also they are what we would call indistinguishable dyads. So the assignment of dyad number 1 to dyad number 2 is completely arbitrary in those couples, and heterosexual couples are actually going to be distinguishable because they have gender in our example. That's a distinguishing factor that differentiates partner 1 from partner 2. So for all of those reasons, we had to eliminate those folks. So now that we've specified our 2 latent factors, again, this is dyadic data, male and female partners, and we're going to correlate the male and female relationship mindfulness variables, those latent factors, and the correlation is going to give us the extent to which male and female partners, how their levels of relationship mindfulness relate to one another. And so if we actually get the correlation between the male and female partners, if we square that, then that will actually give us the amount of shared variance between those dyad members. And then finally, in our syntax, we want to specify those residual covariances. So because of non-independence, and so if you know about the actor-partner interdependence model already, you know that the residuals of the male and the female are correlated. And so that is to account for the nesting of the data, both members being nested within that same relationship. And so we actually do the exact same thing when we are doing dyadic measurement invariance. And so, excuse me, I'm going to correlate the first item in male and females, and I'm going to do the same thing with item 2, 3, 4, and 5, so we can account for that non-independence. So output is going to be our final line of code. We can actually get rid of that bootstrap since we won't be using that here. SAMstat is going to give you your means, your variances, your skewness, kurtosis, 20th, median, and 80th percentiles, all of those kind of bivariate or descriptive statistics. I'm a big fan of the residual matrix, which is the expected values of your variance covariance matrix minus your observed values, and the extent to which those differ can provide information about what parameters are overestimated, what parameters are underestimated, and that can have implications for how we potentially revise our model. Tech 1 is simply Mplus giving a label or a number to every parameter in our model, because sometimes if we get like a non-positive first order product derivative matrix, it'll say there is, we can't invert anything. And so there is a big problem. And so go see parameter 67. And so we don't really know what parameter 67 is in our model off the top of our heads, because one, it's hard to keep track of that. And 2, we don't really know how Mplus creates those labels. And so the Tech 1 will tell us what parameter that is. It'll tell us, oh, it's the covariance between X1 and X3. And so we can go there, and that allows us to start our investigation. STDYX is standardizing your X and your Y. So these are fully standardized estimates. And you have mod indices, which are modification indices. So if there are model misspecifications that Mplus senses, and a lot of times they can be nonsensical, but it will provide every single piece of information about, including omitted paths that would potentially increase the fit of our model. And so I want to know what Mplus is kind of thinking in that way, because maybe there is something behind what Mplus is telling us, and perhaps maybe there's not, but I want to just have that information. And then C interval is confidence interval. So it'll give us the 90th, 95th, and 99th percentile for our estimates. And so now we can begin to jump into our actual analyses. So we can go ahead and just hit the run button. And we'll see that we have 305 observations. So remember, because we are in wide format, each dyad has its own line. So this means we have 305 dyads, which means we have 610 people in this sample. We'll scroll down, we'll look at covariance coverage. This tells you this gives you bivariate information about the extent to which there's missing data across all pairs of variables. And so as you can see, we have, it looks like at least 99.7% coverage on all of our variables. So that means we're probably missing one, maybe two cases. So missing data in this data set is definitely not a problem. We have our sample statistics. So we have our means up here for each variable. We have our covariances, which are difficult to interpret because they're in the raw metric of whatever the relationship mindfulness scale is measured on. I believe it's a 1 to 7 Likert scale. And then we have, last but not least, our correlations, right here and here. Here's our univariate statistics. Again, I look at these actually quite frequently, not because they're a great source of information, but if there is a syntax error, a lot of the times it will show up here. So for example, if I miss that 999 code or the negative 999 code, I will see a negative 999 here for the minimum value. All right, so that tells me that my syntax is incorrect and I need to go back and revise the model and add that piece of information. So what we will do is we will go down to our model fit. So you want to see this model estimation terminated normally output message, and you don't want to see anything else underneath, because sometimes there will be warnings underneath the this message, but we got nothing. And so this tells us that we have proper maximum likelihood solutions. So for configural invariance, again, we are just testing the factor structure of the relationship mindfulness measure across men and women. So essentially what that means is we are trying to say there are the same number of latent factors, there are the same number of residual covariances, there is the same number of items. You want to make sure that they are actually identical, all right? And the way we test configural invariance is essentially through model data fit. And so this is the chi-square test, and we want this to be non-significant. Oftentimes this test is, or not oftentimes, it is highly overpowered. So even if we have a significant value, that's not a nail in the coffin that we don't have configural invariance. But it's a piece of information that we use in order to determine whether or not we have configural invariance. Another piece of information that we use is the RMSCA. And so we generally want this to be below 0.05 or 0.06. You'll see various guidelines. There are no hard and fast rules, Rather, the RMSEA functions differently under different conditions. Notably, it's profoundly affected by the number of degrees of freedom. So in small degree of freedom models, oftentimes, which can be a CFA, the RMSEA performs quite poorly. But we actually have a relatively decent size in terms of degrees of freedom. So the RMSEA is I'll probably use that in my interpretation of whether or not we have configural invariance or not. Right. When you get into kind of single digit degree of freedom models, that's when your RMSEA is either 0 or it's like 0.10 and above. So there's not really too much in between. We want CFI and TLI values of 0.95 and higher. That's based on the recommendations of Hu and Bentler, which is probably one of the most cited, if not the most cited, structural equation model manuscript ever written. Most people apply it incorrectly, and they overgeneralize these recommendations. But our model is actually really quite close to what they tested in their simulation study. I believe they use it was a 2-factor model. I believe there's 4 indicators on each factor. And so we're actually pretty close to that. We have small differences in that we have an extra item and some residual covariances. But for the most part, we're fairly close. We're way closer to what Hu and Bentler tested compared to like a path analytic model where there's no latent variables and there's paths missing and things like that. So we're relatively close. And again, it's a piece of information to have. And then finally, we have the SR-MR, which is the only fit statistic that is presented here that we'll look at that is not based on the non-centrality parameter, which is your chi-square minus your degrees of freedom. All right, and so the SR-MR, my anecdotal experience has been, it's pretty much always good for the most part. Very rarely will I see this fluctuate in some substantial ways. So not a whole lot of weight is placed on this, or at least I don't place a whole lot of weight on it. It's just kind of something I'm monitoring. So we can actually scroll down and look at the factor loadings and the results. But if we have a good model data fit, and we actually have excellent model data fit, then we don't really need to do that. But I like looking at the factor loadings just because it allows me to kind of get a good sense of what might be coming next. Because next we're going to test metric invariance, which is where we're going to constrain these factor loadings to be equal across men and women or male and female. And so by eyeballing it, I might be able to tell whether or not there is going to be a potential problem. So if this, and I don't see any potential problems, they're all really quite close to one another. But let's say this one was, instead of 1 point, whatever it was, this is 2.517. Again, this is unstandardized. Then I could say, oh boy, I can imagine that this factor loading, this difference between male and female on that 5th item is going to be quite substantial. And so I'm kind of anticipating metric invariance potential problems there. And so if we do encounter those problems, then I can go back and I can say, oh, let's start with item 5 and see if that's the problematic child of the 5 items. So it is worth a gander, but again, I don't place much interpretive value on these results. And again, these are unstandardized. And if we scroll down, we will get those standardized results. And these are in metrics that are probably more familiar to us. These are essentially equivalent to beta weights in structural equation modeling and path analyses or in linear regression. They're interpreted the exact same way. All right, so that is, actually, I'll scroll down and I'll show you what the residual matrix looks like. And so there's a couple of parts in the residual matrix that I look at. I look at the residuals for the correlations. So this gives us kind of an effect size, a magnitude of how much our individual parameter estimates, our correlations are over or underestimated. And then we actually have a z-score for those to see whether or not that is statistically significant. So if you have a positive value here, that means you have overestimated the relationship in your model. And if you have a negative value, that means it is underestimated, right? And so occasionally you will actually see 999s down here in the z-scores, and that's because we are perfectly reproducing the variance of RMM2 for the men. All right, so these diagonal elements, they're going to be variances. All right, because this is the variance covariance matrix, or I guess a correlation matrix. And then if you want your variance covariance matrix, it's up here as well. But again, you see that we have perfectly reproduced the variance of that that second item for males, and so there's not a statistical assessment that we can run for that. So if you remember from your first statistics course, you probably remember your critical value for your Z is 1.96. And so we want to look for any outlying values that are 1.96 and above. We are most likely going to encounter those in some way, shape, and form because, again, these tests are extremely powerful and extremely sensitive. So just because we have something above 1.96 doesn't mean we really need to make any changes. But if we have some pretty substantial outlying values, then that is something we would need to consider. And so I'm looking here and I see one that's significant here. And so that means the association between or the correlation between relationship mindfulness, that first item for men, and the fifth item for women is currently underestimated, and it is significantly different from 0. And if we look up here, we say it's underestimated by about 0.10 in terms of magnitude. So that could potentially be something we want to look at. I see another one right here. And so relationship mindfulness, item 3 and 2 for men, that corresponds to a correlation of negative 0.08. So again, that could be fairly substantial. And I see another one over here of negative 0.4599. And I look, that is between 4 and 5. So I look up here. And between 4 and 5, and it's 0.04. So the magnitude isn't as big as the other ones, but we actually have a lot more precision in our estimate. That's why the Z value is so much higher. So overall, I might keep an eye on a couple of these, but for the purposes of this video, just being really about testing measurement invariance, then I'm comfortable moving forward and really just kind of monitoring these guys from here on out. And the residual matrix isn't something that I will routinely check every single time, but since your metric and your scalar models are being compared to your configural model, I want to be really, really sure that our configural model is the right model and that we don't have any glaring misspecifications, because every subsequent analysis we do is based on this model. If it's wrong, then every subsequent analysis is wrong, and we could run into type 1 and type 2 errors. All right, so now we are going to shift over to metric invariance. And so you will see everything from here up is identical. Nothing has changed in the highlighted region. The only thing that has changed is right here. And so what I have done here is I have added labels to the end of each parameter. And you'll notice that in the previous model, I had everything on one line, but one of the idiosyncratic characteristics of Mplus is that when you add value labels, you need to have them on separate lines, all right? And so I just hit enter, 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 and added the value labels in the male model, and I added those exact same value labels in the female model. So what we're doing in metric invariance is we are constraining the factor loadings to be equal across the groups. So we are saying the relationship between the underlying latent variable of relationship mindfulness and that first item, and we'll just go with that first item as an example, is exactly the same for men and for women. All right. And so if that is supported, then we have that item is invariant, and that's kind of what we want. That means that item is measuring that construct in the exact same way for men and for women, which is hopefully what we have, and makes our subsequent analyses a whole lot easier. On the other hand, in the social sciences, it is quite common for us to have non-invariant items where some items operate differently for men and for women. And so we can have what's called partial invariance. And what we have is some items, perhaps let's say these three, are invariant across gender. But then these last two items are non-invariant across gender. And there's what we call differential item functioning. Or another way to think about it is, in our example, gender moderates the relationship between relationship mindfulness and item 1 and item 2. And we have a non-linearity there. So that tends to be the easiest way I like to think about it, is if we have a non-invariant item, we have a moderating process that is happening across the grouping variable, which in our example is gender. And so again, you will add these value labels to the end of each factor loading, and you want to be sure that they're identical across male and female. So that first item, it should be A1, and this can be anything. So you can really create any value label you want. I just chose kind of A1. So that first item for males is constrained equal to the first item for females, and the same thing with 2, and the same thing with 3, and so on and so forth, and you kind of get the picture. If you accidentally had this, then all 3 of these would be constrained to equality, and that's not what you want. If this factor loading and this factor loading and this factor loading aren't significantly different from one another, you may never notice that there's this misspecification or miscoding. But if you get some really wonky result, it might be because you have, again, a minor syntax error. So you want to be, again, really sure that you are double checking your labels, and that you're ensuring that all the labels correspond to the appropriate pairs of items. And then everything else down here is exactly the same as in the previous model. So what we will do next is we will go ahead and run this, and we are going to see whether or not we have invariance. And so, again, everything else is looking the same. So making sure I have the same number of dyads, same covariance coverage, descriptive statistics, everything looks fine. And so I can actually go down to model data fit, and this is going to be where we begin to accumulate evidence for whether or not we have invariance. And so I will actually split screen here because I want to look at the results side by side, because we are going to do in our heads a chi-square difference test. I will give you the answer at a very general level, but you would actually need to do the difference test using an online calculator or the diff test option in Mplus. But for the sake of this, I'm not going to go through that. I'll just kind of give you the answer because it's actually going to be quite obvious. So your chi-square test is going to be your what is most commonly used to calculate a difference test. Other people will advocate for a delta CFI. And so with a chi-square difference test, you want it to be non-significant, all right? And with a delta CFI test, you want your reduction in CFI to be less than 0.01, All right. If it's greater than 0.01, then you have a significant decline in model data fit. There's a paper in 2002 by Chung and Runsfold. I believe I'm butchering at least one of their names, but it was in structural equation modeling, and it's again one of the most highly cited invariance tests and papers within structural equation modeling. So we have a 4 degree of freedom difference between these models, all right? And so that is the correct amount of difference that we want. And so what we are going to do is we are going to look at a chi-square. It follows a chi-square distribution. And so there's going to be a critical value associated with 4 degrees of freedom on a chi-square distribution. And I don't remember the exact number. It's somewhere around 12 or 13 or 14, somewhere in there. Perhaps it's a little lower. But our chi-square only went down by 1.5, right? So with 4 degrees of freedom, our chi-square only decreased by 1.5. Clearly, that is non-significant. So I can confidently say that that by constraining the factor loadings to be the same across gender, that does not significantly harm the model. Likewise, we have a CFI change of, 0.002. So that is quite a bit smaller than the 0.01 threshold that has been documented, but again, by Chung and Runsfold in 2002. And so we can go in and explore the findings. Again, I don't necessarily place a whole lot of value on the findings at this point. I'm mostly looking at the invariance test. I'm just kind of holding the findings kind of loosely in my mind. And we'll first take a look at our unstandardized results. And you will see they are identical for males and females. And again, that's because we added those value labels, those model constraints. And so this is actually a nice way to check your syntax, is if any of these are different. So you have 1 and you have 1, that's by default. You have 1.25, 1.245, 1.245, 1.235, 1.235, so on and so forth. Then you have correctly coded your model. And then you can, again, take a look at the intercepts, because that's actually what we're going to be testing next, to see if you can get like a spidey sense to see if something is incorrect or not, or might be potentially problematic. I'm not seeing anything, just kind of eyeballing it, 3.63, 3.61, 8.7, we have 8.4, we have 3.913, 3.885. So everything looks like it's probably going to work out, but you never really know. But I feel pretty confident about that. And then we can scroll down here to look at our standardized estimates. So as you may or may not know, that when you are constraining paths, you're constraining only the unstandardized estimates to be whatever value it is that you specify or that the model kind of estimates. So your standardized loadings will always be estimated. All right, so we can finally move to scalar invariance. And so scalar invariance involves a couple of extra steps. So first, again, up here, all the highlighted, exactly the same as the metric model. So when we're testing measurement invariance, all of these models are going to be hierarchically nested. So you are gradually placing more and more and more and more restrictions on the model. So the restrictions you put on the previous model are kept in all subsequent models thereafter. So, for example, we have the factor loadings constrained to equality across gender in our scalar invariance, which is again testing item intercepts. All right. So we are keeping the restrictions that we placed on the model in our metric invariance test. So to specify and to estimate scalar invariance, we are going to need to explicitly code in those estimates of the intercepts. And if you are dealing with means or intercepts in Mplus, you will be using brackets. So you will see that I have bracketed every single item. And again, all of these are the 5 male items. These are the 5 female items. And the B1 label is just because that's the next invariance step. So I went from A to B. And if I was going to test strict invariance, I would go to C next. We're not going to do that because there's not many benefits to strict invariance, and we don't really need it in our models that we are going to be estimating. Generally, scalar invariance is enough, and oftentimes just metric invariance is more than sufficient. So what I've done here is, again, B1 for the first item intercept for females is exactly the same parameter label that I have for the first item for males. Same thing with item 2, 3, 4, and 5. And so that is the way you would code in your or constrain it your item intercepts. The other thing that we are going to do here is we are going to estimate that the latent mean difference between relationship mindfulness for males and females. And so how we're going to do that is I picked the female relationship mindfulness kind of arbitrarily. That might not always be the case for you, but in this example, it doesn't really matter whether it's male or female. But let's say you are doing invariance testing across treatment and control. Again, that's not necessarily applicable to dyadic data, but let's just say, for instance, then you would probably want your control as reference, and you'd want to specify your treatment. Again, it doesn't actually change your results. It might just flip your sign, but everything else is going to be the same. But it's unnecessary confusion for you if there is meaning in your dummy coded variable. So here I am going to throw brackets around rem-fem, which is the latent variable name, right? So it's up here. And I'm going to throw an asterisk at the end of it. So if you're throwing an asterisk at the end of it in Mplus within the context of structural equation models, that means that it's going to be freely estimated. It means something a little bit different in Monte Carlo simulations, but we're not necessarily going to go into that here. So for our intents and purposes, this little line of code, brackets, latent variable, star, or asterisk, close brackets, and semicolon, that tells Mplus I want to freely estimate this latent mean. And the results that we get are actually going to be a mean difference with the males in our example. And then everything else is identical. Nothing else has changed. So we can go ahead and we can run this model. I'll say yes, and hopefully I didn't change anything too significantly. All right, so same number of folks, same covariance coverage. All right, mins and maxes look good. And so we can actually, we'll pull this up next to the configural. So in this model, this is the configural. So these were our fit statistics, or not configural, this is metric. These are our fit statistics for metric. And what we did is in the scalar model, we gained 4 additional degrees of freedom. And so our chi-square went down by about 1, which again, if you know your chi-square distributions, you know that a chi-square with the critical value for 1 degree of freedom is 3.84. So clearly, even if we only made 1 parameter change, that would still be non-significant. So clearly we have invariance from scalar to metric. And so what that means is that by constraining the item intercepts to be equal across groups, we did not induce or cause significant harm to the model, all right? Which is a great thing. And so what we can do now that we have scalar invariances test latent means. And so generally you might think, when am I ever going to do that? I'm just more interested in the relationships among other variables. But let's say you're interested in change over time, so you're going to run a growth model. Well, those intercepts and those slopes are actually latent means within a structural equation modeling framework, and you will actually need to have scalar invariance in order to run those models. Otherwise, your estimates of your slope and your intercept are going to be incorrect. They're going to be biased, and unfortunately, you'll be modeling nothing more than measurement error. All right. So if you were doing anything with growth, with any type of growth modeling, you will need scalar invariance. If you're doing latent change score models and things of that nature, there can be mean structures involved in those types of models. So even an ANOVA or repeated measures ANOVA, or even a t-test, all of those are going to involve means. And so you would need scalar invariance for those. And we have scalar invariance. So we are good to go in all of those different sets of circumstances. All right. So essentially, that is the way we estimate invariance within Mplus. Hopefully this was helpful in some way. And again, let me know if you have any questions around the invariance testing process in general, or how you use Mplus to estimate those different procedures.